about designing microplastic binding peptides using hybrid quantum classical approach. So let's first read the abstract together.
What do you think? Every fancy word there. Oh yeah.
I think the sentence with the word gap in it.
Yeah, clearly the gap, right?
Yeah.
There are yeah. Jay loved the gap sentence in Korea. Good.
Yeah, so de novo means from the beginning. So they want to design some peptide to protect some pollution thing. They try to use hybrid quantum classical method.
So before it actually, de novo design of peptide is very challenging. Only a couple lab in the world can do it. De novo means from the nothing. You use just computer simulation to design something without any experimental data. That's very challenging. And everyone, what do you think in this abstract? Which words are very attractive to you? What made you this manuscript paper is interesting? Just tell me a keyword. What made you this is very interesting? That's all? Which word do you like? Yes, quantum computing, yes. Yeah? Okay, good. Number 2, any others? Pollution? Plastic pollution matter or not? Matter, right? And de novo peptide design, that is also very good word. So, kind of why I like this abstract is there are 3 things. What they will do is de novo design, very important problem, and their approach, quantum computing. Finally, what is the indication? They can resolve the plastic pollution. You like it? Yes.
Okay, so first let me give you an overview of what they did. So basically, they want to generate peptides that are fairly nice. So what is peptide? Peptide is some chemical compound which looks like this. But unfortunately, I will not focus on this chemistry. So instead, so they want to generate this peptide using computer. So what does generate means? They try to use the generate neural network, in particular the variational autoencoder. So this is the data, given data, we have a peptide. So we want to generate some probability distribution. So from this distribution, we want to sample to generate a new one, like this. So, but in the title I said, the peptide should be fairly nice. What does fairly nice means? Should have high binding affinity. So I will not focus on its chemical background. So you can just think about a number. There is a number which which means the binding affinity score, it should be low.
You mean the dissociation constant? So
Uh,
high binding affinity, low binding affinity score. Why they are important?
So there is a score which tells you how much the binding affinity is,
Mhm.
and this score should be low.
To make a high binding
Yes,
affinity?
yes.
Okay.
Yeah.
So can you tell me about this autoencoder? So the data means what kind of data? Just sequence or?
Yeah, the peptide is transformed into sequence of 1 or 0.
1 or 0?
Yeah.
How they 1 or 0? Actually, I don't understand. How can we make the because peptide is a sequence of alphabet.
Yeah.
How can we because pink will be something and then green will be something else and then yellow will be right? There are amino acid about 20 things, so their color will be one of the 20. How they change it to the one hot encoding?
Yeah,
They have 20 different columns for the amino acid one type. Is that what they did?
actually, I didn't check the one hot encoding part. I checked I want to introduce the middle part.
You could
Yeah.
have 26, a vector of 26, let's say there's 26
Amino
amino
acid,
acids,
yeah.
right? So then you have sequences of 26, like blocks of 26. So each amino acid is a
It has a
chain.
matrix, right?
It's a single one
Mm,
in a block of 26.
yeah.
You chain them together.
And then another important thing is affinity score. So they not only plug in the, I think, one-hot encoding, they also put the sequence affinity score, 32.54.
It's deduced from,
Do they also plug in the existing peptides' affinity score?
yes. They compute the peptide score, and it is not in this paper, it should be from another paper.
Yeah.
Anyway, they should put in the score of the data.
So then this machine neural network goal is predicting their affinity or what?
Generate a peptide which has low score.
Low score. Oh,
Yes.
okay. So this when you understand the machine learning. Basically, machine learning is micro f of x, correct? So if everyone, when you explain the machine learning or deep neural network, the three components should be very clear. If we're missing the one of these three, not understandable. Clear? So here, at least, it could be wrong, but x is matrix 26 column, the length of the peptide, amino acid of type 1, 2, 3, depending on if first position amino acid is 1, then it'll be here 1, 2, 2. I'm sorry, 1, 1, 1. In this way, we can convert the sequence to the matrix, which looks like an image, right? Clear? And plus, they also plug in the affinity. So affinity means this protein has an affinity score. So basically, for protein chain is converted to the what? Matrix image, either 0, 1, and each matrix image has assigned binding affinity, right? That's their plugin, at least. I don't know, it could be wrong, this is our x, and you need to explain what will be f and y.
Yeah. It will be explained continuously later. So the goal of the paper is to generate a peptide that has low binding affinity score. By generate, they use variational encoder. It is the classical way of the computing. To get the low binding affinity score, they use what is called the variational quantum circuit. It is the quantum one.
What is? Can you explain what the red means? Sorry. For what they use variation quantum circuit?
Low binding score. So here I said, in order to obtain high binding affinity, this score should be low.
Okay.
But I will not tell you about the definition of binding affinity score. I want to tell you about this mechanism of this variational quantum circuit. So basically, in this variational autoencoder, if you have an input, then it is transformed to the latent space, and then it's decoded to generate some probability distribution. In the probability distribution, you sample the candidate peptides. But here, in order to obtain the low binding score, we should add some architecture here in the middle, in the latent space, and that's where the variational quantum circuit is used. I'll tell you about this. So basically, goal of the journal club is to introduce the concept of this variational quantum circuit. Okay. So in order to understand this quantum circuit, let me start from the very beginning of the quantum mechanics. So in the classical physics, the energy is defined by the function like this. So here, 1/2 V squared is the kinetic energy, and V of x is potential energy. So using the energy, you can define the equation of motion like this. For instance, if you have the potential energy like the square of position, the above V should be P, it is the momentum. So then you obtain the equation of motion like this. If you draw the phase space diagram, you can see the rotation of particles around the circles. Now it is transformed into quantum mechanics like this. First, the energy should be transformed like this, operator. So the energy H now becomes the operator H. So operator means the input of the energy should be a function, and the output is a function. So I will skip here. So Hamiltonian or energy is now no more a function. Now how to get the equation of motion? Surely it looks like this partial differential equation. This is the Schrödinger equation. Here the psi is called the wave function. And for instance, in the harmonic oscillator, the energy Hamiltonian now becomes here. So what's going on with this? So at the first sight, it looks very strange. So let me tell you why do you need this. So starting from the Schrödinger equation, we want to compute the observable. Observable is the physical quantity, okay, like energy, position, and momentum. So how they are computed is by taking the expectation. So quantum mechanics is probabilistic, so in order to get some physical quantity, we should take the expectation. It's defined by some inner product in the second formula. If we do this for the harmonic oscillator case, then the equation of motion is like this. So this you just see before. So here in the classical part, we get the equation of motion like this. If we use the Schrödinger equation and take the expectation, then we obtain basically the same thing in expectation. So here, what is psi? What is wave function? Indeed, this amplitude, square of amplitude of wave function is something like a probability density function in quantum mechanics. So in order to be a probability density, this integral should equal to 1 for the whole time. So it should be preserved. So that enforces the Hamiltonian H should be self-adjoint. Self-adjoint is, do you know the self-adjoint? So in real matrix, it is symmetric. But this should be a complex matrix. So self-adjoint means symmetric in complex matrix. Okay. So from the Schrödinger equation, we basically can solve this like the following. And since H is self-adjoint, its evolution is unitary. Which what does it mean? Do you know unitary matrix? Unitary. It should be. So for instance, M is like this. Then M dagger is like a transpose and then take a complex conjugate. Unitary means unitary is similar to orthogonal in complex application. We should satisfy this relation. What I want to say is that in quantum mechanics, the evolution of a particle should be unitary or evolution. We will use this later. So let's go to. So our goal is to understand here the quantum circuit part of this variational quantum circuit. So let's understand this one by one. So let's start from the classical logic. What is a bit? Bit is a number, 0 or 1. Okay. What is many bits? Many bits can be a pair or many pairs of bits. So it can be like a sequence. Then what is the quantum analog of bits? We start from the Schrödinger equation. So originally when I explained this as a dynamics or a physical thing, the domain of this wave function, if you ignore the time, should be any Euclidean space like R1 or plane or something. But the bit only takes 0 or 1. So its elements are 2 sets, 2. So we want to restrict the wave function's domain into this following set of 2 elements, 0 or 1. So we want to think about this function. Its function, since the domain has only 2 elements, it is completely determined by the 2 numbers. Okay? 0 and 1. It means that psi is basically a vector in 2-dimensional vector space. 2 pairs determine the wave function. But if you recall, since this is a probability density, this integral should be 1. But if the domain is 0 and 1, is this equal to, say, this? So we have a restriction of the function. Okay? So now we can define qubit. So qubit is a vector in 2-dimensional space with a restriction like this. Okay.
So qubit is R2 comma beta in the C2 dimension. So just 2 complex numbers.
2 complex numbers.
And then their length is 1, basically.
Yes.
Okay, so it's basically, if we draw this unit circle in the C2,
Yes.
X-axis is C, Y-axis is C. We can draw the circle, right?
Yes.
So what point on the circle is the cubic?
Yeah.
Ah, why people explain the cubic so difficult? This is so easy. Wow. Everyone is okay about that? Wow, okay.
Yeah. If the previous slides are too difficult, you can just start from here.
What do you think, Jay?
Except for alpha and beta, I think are both complex.
They're both are complex. So X is just, think about just C, also C. Yes. We needed some more imagination. It's a 4-dimensional spaces, but let's just think that S as a X-axis is C and Y-axis is another C. And then the circle. Or complex plane, and four-dimensional circle.
Yeah.
That is a cubic.
Yes.
Very good. Like
So here is the very important notation. Since it is two-dimensional vector, it has a basis, this and this. So we write 1,0 by this notation. And we write 0,1 by this. Okay? This is just a notation, but very important. So basically, all qubits can be written following this linear combination.
and alpha and beta could be C, right?
Yeah.
Okay.
For example, qubits can be done like this. You can see that the square of coefficients sum up to be equal to 1. But what about many qubits? So it's a different story. So let's study this. So many bits are the series of bits. You can just write it like that. So in terms of the space, a single bit belongs to this set, and many bits, for instance, 2 bits, belongs to its product space.
Yes.
Okay? So qubit, although we have a restriction, it belongs to C2. Then many bits belongs to the following space, what is called the tensor product. So what is this? I will explain you. So basis of C2 was 0 vector and 1 vector. So the tensor product will be explained in terms of the basis. Then the basis of this space looks like consists of these 4 symbols. So what is this? In the first part, you can take either one of these. In the second part, you can also take either one of these. So we have basically 4 combinations of these basis elements. Okay, so this is just a symbol, but actually you can just think this tensor product of 2 space becomes C4. Okay. Question. So here 4. What is 4? 2 plus 2 or 2 by 2? What do you think? 4. Is 4 2 by 2 or 2 plus 2?
By
2 by 2. 2 by 2. Because we have a combination of bases. Actually, we also have the following formula. So if we tensor product 2 matrices, we can compute it using like this. We have this formula. So, conclusion, n qubit space. So we need n tensor product of this space. So it is basically 2 to the n dimensional vector space. Okay, so let's recall this picture. So how much did we get? How much can we understand? We went here. We at least understand this part. So let's move on. let me give you two important notions. Before that, let me tell you a property of tensor product. So if you want to compute the following tensor product, you can work as if you are doing the inner product thing. So it means that it is bilinear. So you can compute first the second component. You can expand it with this, and then you can also expand it in the first component. Now, a separable state means that a quantum state or a qubit which can be decomposed by the two tensor product of other smaller ones. For instance, it can be like this or this. These are all separable states. This is just the definition.
Oh. We can have these two tensor actually.
Because we regard the whole thing as one. So
Oh.
then it is decomposed by this.
And what is the dimension of that? C
This is C2, C2, so this is C4,
4 and then C6 then. C8 or
C8.
C8
The dimension should be multiplied.
multiplied. Okay. So then first is C4, second is C8,
Yes,
third is C4.
yes, yes. Of course, this is not qubit because we don't have the coefficient condition.
Oh, not the qubit. Oh,
Because
because
we,
they're
yeah,
it's not in the circle.
yes.
The length is not the one.
Yes,
Oh.
I'm just explaining this for tensor product. So now the entangled state is defined as follows. It is something that is not separable, something that cannot be decomposed. For instance, we have this following a vector, or there are famous states which is called the value states. They cannot be decomposed. Question. So is this entangled or separable? What do you think? Separable?
Separable.
Why?
You can use variability to make it like a book.
So I expected people think this is entangled because it looks complicated. But indeed, if you look at the book, it originated from this. So the lesson here is that determining whether the state is separable or entangled is not trivial, not easy. There are some criterions, but it is not our focus today.
인수분해를 잘하면 되는 거예요. 세퍼러블인지 아니면
뭘 그렇다고 볼 수 있고. 근데 복잡해지면 쉽지 않은.
결국에는 인수분해 문제랑 똑같은 건가요? 뭐 곱하기 뭐로 바꿔야 되는 거예요?
네, 그렇죠.
So yeah, it's about factorization.
Yes. So, in the beginning, I mentioned that evolution of quantum.
I'm sorry, by the way,
Yes.
why the separable and entangled method?
I will tell you later, but
Later? Okay.
but that I will not tell you deeply, and I don't know deeply, but so in neural network, so you can imagine the fully connected nature of neural network.
Okay.
It makes all the components in some sense highly correlated.
Okay.
Entanglement is
That state?
something like that. So makes the state highly correlated.
Not separable.
Yes.
Okay. But if it's separate, that means there are two we can separate the network as two independent networks.
Something like that. So if something is separable,
Yes.
then if we do perform some transformation here, then it only changes this part. But if it is entangled, we cannot only change the part of the whole thing. So that's yes. So quantum evolution should be unitary. What does it mean? Unitary, as I mentioned, we should specify this. What is evolution? So as we are dealing with qubits, qubit belongs to C2. Evolution means just the transformation of qubit to qubit. So C2 to C2.
So actually movement in the circle, one position in the circle to another position.
Yes, yes. So it should be linear transformation, but so qubit should be in the sphere or circle, but it should be unitary to preserve the length. So in case of one qubit, this is just a white matrix. In case of many qubits, for instance, if you have 2 qubits, I mentioned this is C4, we have 4 by 4 matrix. In general, we have 2 to the n by 2 to the n matrix.
So this is now 4 by 4. This will be
This is 4 by 4.
4 by 4 matrix, right? The 4 by 4 matrix is sort of block diagonal matrix, or just really whole 4 or
4, 4, but unitary.
unitary, and block diagonal 2 by 2, 2 by 2, or everything is filled.
No restriction on black diagonal.
Okay, gotcha.
So for instance, it can look like this. It can look like this. So it does not need to be block diagonal. So quantum gate is just the transformation of n qubits. So it is just 2n by 2 to the n unitary matrix. The word quantum gate is another important notion. But why the name gate? I will tell you. So let's go back to the classical bit. So we start with 0. Maybe in the computer class, you learn the series of gates like NOT gate, AND gate, OR gate, or something like that. So if we perform the NOT gate to 0, then what do we get? We get 1. So we deny the state is presented. In terms of the function, we have this. So a function is defined on 0.1 to itself, and we simply add 1 to the original one. Maybe you know, so what happens if I start with 1, then we get 2? Yeah, you know this? Okay. Let me give you another example. We start with 0.1, so 2 bits, and we perform the AND gate. AND means that, okay, I will tell you like this. AND means that the 2 inputs should be all true to get the true one. Okay. In terms of the function, you can simply multiply the 2 inputs. So this is a classical gate. So now let's go to quantum gate. So unlike the classical gate, the domain and the range can be different, but in the quantum case, they should be the same. In other words, it should be an action on the n tensor product of C2, so n qubit space, and it should be unitary. So for instance, let's study the NOT gate. So NOT gate is usually called by Pauli X gate. Pauli is the name. And there in quantum gates there are several symbols to denote the gates. Here should be input and here should be output. And in terms of the matrix, it can be written like this. So what does it mean? So NOT gate is a function, unitary function from C2 to C2 and defined by the matrix 0, 1, 1, 0. So for instance, you get this. You get the point. So it should be 1, 0. If you compute this, you get 1. So you deny the state. You can also compute this. So next example is famous one, Adamar gate. It is also defined on one qubit space by this matrix. If you perform Adamar gate, then you get this. What is this? So if you just plug in this zero vector, then we get the combination of two states with equal probability. Okay? So this is often called as superposition. Superposition means that in quantum mechanics, two different states can be in some sense together before you observe it. Another famous gate is a rotation gate, which are defined by a series of matrices. I will not gonna go in this detail. Actually, qubit can be described on the sphere, as the professor mentioned. However, it should be three-dimensional. I mean, yes, because C2 by C2 is four-dimensional, but we have one equation, so it should be three-dimensional. Okay, three-dimensional sphere. So one-dimensional sphere is this circle. Two-dimensional sphere is this. Three-dimensional sphere, you cannot draw it. So if you represent the qubit here in the two-dimensional sphere, it looks nonsense. However, indeed, in qubits, actually only the relative difference between them matters. So we can restrict one more dimension. This is called the block sphere representation. And rotation gates are defined using block sphere. They are rotating the qubits along the XYZ axis. Rx, Ry, and Rz. But this is not our central concern. So let's study a more gate. So from these examples, we only studied the one qubit transformation. Another notable example is C-NOT gate. It's the transformation of two qubits. So using a symbol, it can look like this. And using a matrix, we have the following matrix. So how does it work? For instance, if we plug in this 0 tensor 0, then the output, so what is this? You can use this formula to compute, to make a representation of 0 tensor 0 in four-dimensional vector. Using this. Then you can come back to it itself. Indeed, here these are inputs, these are outputs. What does it mean? So if the left one is 0, then the output is the same. If the left one is 1, then the output of the right one is flipped. So C naught means that depending on the controller, the left side, we do something on the right side. So actually there is a meaning in this symbol representing this one, but this is not our concern. Okay, so let's recall our quantum circuit. So what? Before that we know this. Now this is the rotational gate. And here this is C naught gate. So we know this, this. And they are also the combination of rotation and C naught gate.
What is the meaning of the indexes?
You mean
Zeta in the zeta.
zeta? So good question. In rotational gate,
How much?
so yeah,
Okay.
we need how
Angle.
much you will
30 degree, 40 degree, 60, maybe.
Ah,
But
yes,
theta will
yes.
be not just value, it should be vector.
you mean zeta?
Yeah,
No, zeta is value.
value. Yeah. XYZ has its own angle. But
So Rx means you rotate
along the
along x-axis
pi theta.
by zeta.
Okay.
So that means what is the meaning of the index? Zeta 1, 2, 3.
Zeta. They are parameters. You can think of it like a neural network parameter. Or this. So these are like neural network parameters.
Here in the C naught gate, the input to the dot is controller or
Input to the dot is yes. So this is somewhat reversed. So C naught gate.
Can you go over just first line what it means, like RG theta 1, RY theta 1?
So you rotate
The
the first part in z-axis with this amount.
That's parameter.
That's
Neural network parameter.
yes.
And then in the Y direction,
Yeah, you also
rotating another angle.
Yes.
And then that's the X or Z.
G.
Again Z. Why?
D1.
Why not X?
Actually, I don't know why this is constructed like this.
It's everything is Z, Y, Z. So they rotate in the G direction, and then Y direction, and then G direction. Do we have only two directions?
No. We have two sections, but they do.
X가 없지 않아?
But actually, yeah.
Only two? Two dimensions? Because what is dimension? It's a C2, or what is the input?
Input is C2.
Just C2, right? So that's why I thought that it's just X, Y, and Z.
No.
It's a 4.
So I didn't include that, but okay. The qubit should be a complex vector in C2. Okay. So, but it is then a vector in R4. Okay. So it should be a three-dimensional sphere in R4.
So it's basically a 4-dimensional space, right?
Three-dimensional
sphere.
But yes, but you cannot imagine.
Yeah.
Yes.
It's a confusing way.
Yeah. And then that means we have a rotating or 3 axis or 2 axis or 4 axis.
But we can reduce one more dimension. I didn't include it, so that it can be represented on 2 dimensions. Sphere, like this,
Okay, so then we have a XYZ.
X, Y, Z.
Why they should not rotate the X?
But actually, using the two rotations of x, y, you can generate the
Other
another-
rotation is a trivial.
Yeah.
Okay, so that's why we just need to tune the two parameters.
Yeah, I think that if we combine the two R rotational matrices, then we can
Which
produce
is
the.
another thing,
Yeah.
okay? Then that explains why we don't do the x, but why they do the z, y, z. Do you know any physical meaning for that? No.
No, it's a typo.
Typo? But they, look at the color. Every yellow color is like Z. So every orange color is Y.
Yes.
I think there should be something is going on.
yes, there should be something. But
Yeah, I know, we have only one physicist.
Kangmin?
Gangmin, we don't have Gangmin here. Kim? Yeah,
그냥 듣고 있어.
Gangmin is listening. Gangmin, can you hear?
oh,
Yes, I can hear.
Yeah, explain this. Physics.
I think I need some time to think.
What about we have a chemistry person here? June? You learned the chemistry. Any idea? It's crazy. You participate suddenly gave the z over minus say over b over 2 and then wow.
it's something like a neural network black box, I think. I'm not sure, I should study.
So yeah. 진짜 저게 자연스러운 거지.
But indeed, do you know universal approximation in neural network? Neural network has a universal approximation property, means that every nice function can be approximated by a universal neural network.
Quantum can be also approached like just this.
I don't know the exact statement, but they said that using this rotational gates, they can make some universal approximation.
Oh.
There are some conditions. But we also need this CNOT gates to make them entangled, make them mix.
I see. Basically, this is a design
Design, yes.
which can make any type of the basically approximate function for quantum.
Yes, maybe. This is why this called answer.
저렇게 하는 이유가 있구나, 그러니까. Maybe that's the trigger thing for that. Kind of like
Maybe.
yeah.
These are quantum gates. And quantum circuit is a collection of quantum gates to make something.
Basically, what that means is we plug in the 4 qubit here, right? 0, 0, 0.
Yes.
By plugging this 4 qubit, if they passing this circuit, we can reach it to basically anything, I guess. We can fit the any state in this 4D C2 space, I guess.
Maybe.
Yeah.
But there is a problem, which I will. So far we know almost everything
Really?
in here, except this mysterious thing. So if you see this, what do we measure? It looks like a velocity measure in your car. It is called a measurement.
Okay.
Oh, I'll tell you. So if you have a classical particle, so I can say something like this. I want to measure the position x. I want to measure the momentum of this particle. I want to measure something like this. We can just do it. And we can also do it many times like this. Measurement 1, 2, 3, 4. it does not matter. So if I draw something, you can continuously measure. However, let's say we have 1 qubit, and I want to, so this is psi, I want to measure some observable. Observable means, I said, position, momentum, energy, something like this. And what do we get? What we get is eigenvalues, one of the eigenvalues is an operator. Here in qubit space, it is a matrix. If we want to observe it, measure it, we get one of each eigen. But as I mentioned before, Hamiltonian should be self-adjoint. Observable should be self-adjoint. Self-adjoint means something like symmetry, complex order symmetry. So if you remember the linear algebra, you can do the spectral decomposition.
Eigenvalues.
Eigenvalue decomposition. You can do the same thing with complex matrices. So this is 1 qubit, so A is 2 by 2. Okay. So we have orthonormal eigenvectors with eigenvalues. So the psi that I want to observe, I prepared, can be represented by this basis. Okay, so if you look at this sentence again, we get one of its eigenvalues. We get one of its lambda or mu. But what does it mean? It means that we get lambda with probability like this, and we get mu with this probability. If you recall the definition of qubit, this sum of these two probabilities belongs to 1. Does it make sense? Yes, this is the measurement.
So the measurement will be either lambda or mu,
Yes.
2 states with a certain probability.
Yes.
Okay.
But there is a problem. In the classical parity, you can measure it anytime. But in quantum mechanics, there is a notion of collapse of wave function. Meaning that if you measure A with psi and assume that you get lambda, so lambda is a eigenvalue for with respect to then the state, original state, collapses to this eigenvalue. So the state changes if you measure it. So basically one measurement alters or changes quantum state.
So stochastic system basically becomes the deterministic system. Original qubit is
Yes.
between lambda and mu. There is 2 states.
Yes,
But if we observe it, then it becomes just one eigenvector.
yeah.
That's Schrodinger's cat.
So yes. If you recall this picture, we mentioned G-basis measurement. What's going on with this? So I will tell you. There is one more quantum gate, which is called Pauli G gate. So the symbol looks like G, and it is represented by this following 2 by 2 matrix. It has eigenvectors 1, 0 and 0, 1, or 0 and 1. Eigenvalues 1 and 9. So if you have a qubit, and if we perform the G measurement, then we can get one of each eigenvalues, 1 or -1. So if we expand it by the basis elements, in other words, we get 1 with probability that amounts to -1.
But we have only one chance to measure it.
Yes,
So actually, we don't know what is our prime data.
yes. However, if we do to many qubits and do this many times, then we can take some kind of expectation, and indeed it will approximate the expectation of this situation. Actually, this is equal to these various quantities. If you remember my slides from the beginning, so this is the definition of the expectation of this observable. From the beginning, I told you something like the expectation of position or momentum or something like this. That one is the expectation of this Pauli matrix. So the more you did, you will gradually approximate this vector. So from this circuit, we know this, and we finally know this measurement part. In the end, we get the eigenvalue, which is the classical number, real number. So yes, we understand many things, maybe some, but almost. So what do we don't know? We don't know here. So far is the introduction to quantum computation. Actually, there is a famous example showing the power of quantum computation, which is called the Deutsch algorithm. Deutsch is not German, it is name of some English professor. I will just explain you the problem. Let's say I have a function, the n plus 0 or 1. Let's say we a priori know that f is either constant or half, meaning that we have a n combination as an input. So half of them becomes 0, and half of them becomes 1. So the problem is that how can I determine where f belongs to? Okay. Okay. Did you understand the problem? Let's say f is n is 3. So n is 3, then it has 8 elements. So I can just write it like this. It means that f is either constant, everything is equal to 0 or 1, or it is half and half. So half of them is 0, half of them is 1.
What about 2/3? Can be 0?
2/3? I mean, we a priori know that where f is either one of two.
Constant or balanced?
Yes. Then how can we decide f is either constant or balanced? This is the problem.
So check the half.
Yes, we have to check at least check 5 elements.
Yes.
So in the general case, we need at least this amount of trials. But the thing is that, thing of Deutsch algorithm is that if you construct a quantum gate, then you can check it with just one trial. Yeah, that's the use of quantum computation. Actually, this problem is not very practical, but it shows the power of quantum computation. If you are interested, you can study this.
So how much faster in this case? Just one trial is enough, I guess.
One trial is enough. Of course, yeah.
What does it mean, one trial?
So if you look at this gate, if you put this qubits and you pass it and you measure something, the result shows you the answer. If you want to do the one pass.
See.
Of course, the speed of performing this, we don't know.
But anyway, the good thing of this design is it doesn't matter about the n, right?
Yes,
Because the previous classical algorithm has 1, 2, 3, 4, 5, 6, 7, 8 or 16, blah blah. The speed will be slowed down. But this gate, this doesn't matter for that.
yes,
n.
yes, yes,
That's the key.
yes.
Oh,
Can search it if you are interested. So let's go to this hybrid building. So the goal is to find a function which gives a score of a latent vector. So we have a vector as an input. It should be 16-dimensional vector. 16-dimensional vector. And we want to get some function which gives you a number. 16 to numbers, input and output. So what does neural network do? You approximate its function by inserting the layers, but we replace it by the quantum circuit we just studied. This. Okay? So we're going to replace it. However, there is a serious problem. I said input is a 16-dimensional vector. It's not qubit. So how can we put here? In order to solve this, we first transform vector to quantum state, and then we perform the quantum circuit. Okay. One way to do this is called the amplitude embedding, which gives you a quantum state from classical vectors. Let me illustrate this using some examples. So given a classical vector, we first normalize it. Again. Then we just simply think the linear combination of qubits using this coefficient. And that's all. But for instance, if you have 3 qubits, can you express it with 2 qubits? 3 qubits. 3-dimensional vector.
Vector to qubit?
Yes,
Two
vector.
qubits, right? 1 qubit, 2 qubit.
Sorry, so we have. Can you express it using this? Only 2.
With qubit?
Yes.
2 qubit. 0 and 1.
Actually, no, we need more qubits. So, but if you remember, the qubit space is a tensor product of C2, so its dimension is always like this, 2 to the n. So the first job should be embedding this in a little bit more bigger space. Like this. Actually, this inside C2 by C2 is a typo. You can ignore it.
CC.
You don't need this. And you normalize this. Then we have a 4 components in C4. So you can express it using the basis elements of C4. This final part is 0, so we don't need it. So this is the amplitude level. So if you recall this picture, I said V is 16-dimensional vector in the paper. So this is 2 to the 4. So we need 4 qubits to express it. So that's why there are 4.
But why V is a 16-dimensional vector? It's a peptide or?
It's a latent vector.
So we reduce the original peptide to the 16-dimensional latent space.
Yes.
Okay, now we make it to the 4 qubit.
Yes.
Okay.
Yes. So far, this is our picture. First, we prepare the input into a quantum state. Then we go through the variational quantum circuit. In the end, we measure to obtain some classical number. But we need, in the paper, there is one additional layer to transmit this to cover some complexity. So this is maybe similar to neural network. This is analogous to neural network. As I mentioned briefly, and I don't understand 100% here, but the highly correlated structure of fully connected neural network can be realized by entanglement or entangled states in this proposition.
Yes, they use the number n for the updating the weight
Number n
and for z measurement
Yeah, they use
to update the weights in the neural network, or just
I guess autoencoder and variational quantum circuit both might be trained.
yes.
Both are, right?
I will tell you.
Coming. Wait.
Before that, I cannot avoid mentioning that I said preparation of input can be done by amplitude embedding. However, there can be a question. If you we will put many arbitrary latent vectors to transform using this 4 qubits. So can you do it automatically? There can be some issue. This can be realized by what is called quantum state preparation. But I only know the word. So let me just remark it. Can be done using quantum state preparation. So now let's do the whole picture. The goal of this was to generate peptides that has low affinity score. And in order to achieve the low affinity score, we need a variation quantum circuit. And the loss function is like this. So y is a score of a given data. And using the variational quantum circuit, we constructed f, giving the input is latent vector, output is each score. This loss function guarantees that function gives you the correct score.
You mean from the sequence we want to predict the correct affinity score?
Yes.
Okay, so
But Dr. Kim gave us a question. How can it be trained? It is trained by the end-to-end manner. End-to-end means that we don't train it separately, but we train it all together. So we combine the loss function was for variational placeholder. I didn't prepare for it, but we combined it together to obtain a score map. Okay. But this is not the end. As I mentioned, we need the score to be low. So after that, we minimize the score function by the gradient descent to obtain some appropriate latent vector. Okay. Get this. Using this, we can finally generate a peptide which has low affinity score. What they argue is that, so this is our quantum hybrid machine. Their score is the lowest among the others. What is this? How they tested is that you replace this quantum part by the classical multi-layer perceptron or convolution neural network. They compared the scores, and they argue that it is lowest. Maybe it is good. I don't know.
So here summary is first they construct the S map which can predict the score
Score, yes.
using that total loss function. So the total
Yes.
loss function means basically we want to predict we want to construct S well,
Yes.
which can predict the score from the sequence.
Yes.
And then furthermore, while we developing the train the S, we want to find the minimum of the S, I guess. What kind of vector can minimize S, I guess. That is a sequence, new sequence.
Actually, what I think is that after we have this,
Yes?
we minimize S again later to obtain this final vector.
Yeah. So
Yeah,
we want to
yeah.
find the minimum of the S.
Yes, that's right.
So quantum part is used for constructing the S or
Yes.
find the minimum of the S?
No, S.
Oh.
This is just gradient descent.
So not only do you have to construct this quantum thing,
Yeah.
but you have to be able to compute the gradient of that observable thing
Yes,
with respect to the input latent vector,
yes, that's right.
which I guess you could say is just the amplitude embedded,
Yeah.
since that's a one-to-one.
So you got the good point. So basically, the quantum circuit. I mean, although in the end we measure some classical number, it approximates the expectation value of the observer. So in the end, it should look like some expectation of something. So it has a function structure, so we can take the gradient. There are some formulas I didn't.
The inner product is certainly not the part that anyone's worried about
Yeah.
differentiating. It's all the stuff in the middle,
Yes.
all the stuff no one here is thinking about because it's all too complicated. Because it's gotta be nonlinear, right?
It's
In
not
some
made.
sense. And to be a good approximator,
By the way, Dr. Wang, so anyway, our input will be chain and then output will be some number, their binding affinity.
Input is chain.
Chain, the chain structure of the peptide. Chain,
Yeah.
why do we need this quantum thing? Kind of original autoencoder might work for that purpose. We plug in the basic matrix, one-up encoding matrix image, and then we want to make their binding affinity value from that matrix. I think that's basically when we have an image, we want to say this is dog or cat or human and elephant. Actually, basically the same problem, right?
Yeah.
So for that purpose, autoencoder has been working well.
Yes, that's right.
Why here they put this fancy quantum thing? Is it really make it better or or they just want to put it as a fancy? Do you know, do they explain why they did it?
One advantage of quantum thing is that they use less parameters than the neural network.
Ah.
But well, you are right. Maybe expensive. So
I see.
So far.
Compared to the multi-layer neural network, this is more simple than for that.
yeah, in
Quantum.
that perspective.
Even if it's 1,000 times slower and takes a team of experimental physicists, they've still used a quantum thing
Because
in a
it's
totally, yeah, isn't that interesting to, maybe this is just pushing forward the using quantum circuits to compute things.
Yeah.
Because I don't know, I'm the reviewer of this manuscript, I may definitely ask, can you compare your one with the classical neural network?
Well, that's what they've done here.
They did it, oh, sorry.
And look how not mind-blowing the,
Which one is, what is it?
This is quantum multi-layer perceptron, CNN.
Oh, it worked well. Okay, better.
But can we 100% trust this? I don't know.
Because there are so many overlap?
I mean, maybe they used some specific data set.
But, I don't know, yeah, so, let's see. Okay, so basically what this shows is, this is an input. So they put like 1,000 peptide structure, and it's a distribution their score. So input average is around here. Okay, from this they learned some S map, but I'm very sure that if we plug in this thing, whenever we trained it, S could be different, I think. So then we try many times so that we find the minimum, and then the minimum of actually convolution neural network is higher than data sets. I think this is a
bad.
bad. But anyway,
Yeah, anyway.
so, and you can see a lot of the, here is very narrow,
Yeah,
there are some cool design exist.
down there in the tails.
So, maybe, I don't know, maybe to understand this protein thing, this quantum might be more natural function rather than just neural network function. Because neural network is also function and this quantum network is also function. The neural network function is real value, quantum function is complex value. But this quantum function might be better choice to describe their relationship. Anyway, the S is a map. Plug in the
Yes.
chain and then output is their binding affinity. It's map function, but for that function, this quantum might be the better design, better approximator, I guess. That's what
It
this.
uses fewer parameters, so
Yeah,
there's
fewer
less
parameter,
parameter.
yeah. Kind of, maybe simple example of this, like if you want to investigate the oscillatory thing, then what is a good basis? Not the polynomial, it should be sine or cosine thing, right? Clear basis. Yeah, of course, if with the polynomial we can approximate the oscillatory function, but we need thousands of the tailored series of the polynomial. But if we use cosine sine, we just need a couple of them, right? Few parameters. So might be that thing could happen here. Wow.
So maybe if we just interpret this, what is that, the quantum circuit as just a function approximator,
Yeah.
then maybe the only advantage could be the smaller number of parameters.
Only on
Is there any possibility that if we make some quantum computer, then or maybe we can
Use this design.
this design more naturally or optionally. Is there anything like that? It's just, I thought my question is it just design or is there any
You can use the
other?
quantum actual computing.
Yeah,
you
computer.
mean, can we actually implement
Yeah.
this? So there are some, yeah, we can implement
Definitely.
only some part. So IBM actually developed some Python libraries that can
Using the
implement,
quantum
yes.
computing.
But actually, I'm not sure whether this is very well.
재밌다.
I think,
yeah.
I think it's interesting that you encode a real variable,
Yeah.
right, with bits.
Yes.
You use a floating point number, 64 bits, right? And then, of course, in machine learning, they want to scale that down. In neural networks, they want to take it down to like 8 bits, maybe. Quantization, right, is what they call that. So now you're representing a real variable with, like, say, 8 or 16 bits.
Yeah.
But this, with qubits, you can sort of represent real variables exactly.
Exactly.
Like, yeah, 4 qubits, you can represent a
16.
vector in up to R4.
Yes. 16, I guess. R16 is it? 4 qubit is R16.
Yeah,
4 qubit is C16.
So yes, it's 16.
but now you don't have this accuracy issue. You're not approximating a real variable with a floating point number. So I don't know how they design these, but practice these quantum circuits. And I'm guessing they just simulate this quantum system on a normal computer chip here.
Yeah. In order to answer your concern, we need to look at the quantum state preparation, the notion of it, how do they do it?
Well, I mean, if they're simulating the quantum circuit, then of course everything's in, ultimately all these operations are floating point operations on 64-bit, I'm guessing double floating point. But I never really thought about representing real variables in a quantum circuit with qubits and how that would work. But, I mean, obviously you don't need 64 qubits to represent one real variable, right?
It's done, yeah.
Oh, it's N?
Yeah, it's the end.
Oh.
Thank you.
So any further follow-up question?
Did they provide about the speed or memory?
Actually, okay, so I didn't include it in my slide, but they did prepare the number of iteration. So actually, according to their graph, the quantum thing, so this is was best. But yesterday I showed this to Dr. Zhu. What do you think? So this is classical. What do you think? Then he said it is lie because we shouldn't compare the number of iteration.
The time?
Yes, time is
So but the quantum computing is coming.
yes,
So this
it's coming,
could be
so it
faster.
can be realized.
Because they have less number of parameters, so they can converge faster in terms of
In terms of
the
number of
iteration.
iteration.
But the most I think for neural network we can calculate the gradient with back propagation. Is there anything we can use like that?
Next
It's
question.
not
So
so difficult to calculate the gradient descent.
there is no notion of backpropagation, but I don't know this very deeply, but there is a notion of shift rule or something, which means that the quantum neural network, its gradient can be explicitly written by the shifts of its parameters. Something like this. It is a function of its shift. I mean, this formula is not exact, but we can do something like this. Do something.
Looks like a finite difference though.
Maybe.
Okay, so when I search it, this quantum ansatz is good for work efficient with quantum computing. Not just a few parameters, it has and then there are different type of quantum ansatz. I think what we see is a chemistry inspired ansatz. There's other thing like
Yes.
hardware efficient ansatz.
Yes.
Some other thing as well.
Do you know how many qubits are in the quantum computer?
I'm sorry. Okay.
Currently,
Currently,
what is Google?
But you might not need that many, right? To do something like this, because it scales exponentially, the vector space you can embed.
실용하면 100만
So
현재
Yonsei University has 127 qubits
Oh,
quantum computer. Yonsei University has
127 qubits.
127 from IBM. I don't know, KAIST. KAIST has a 100 qubit.
Another question is that then why didn't they make the autoencoder with
Autoencoder.
they could autoencoder with the quantum circuit.
Okay. I don't know the deep reason, but as we all know, the quantum computing itself is hard to realize. So people try to combine with the classical method.
So first they reduce the data size using the
Just some limitations. Of,
Okay.
So you only need a 4-qubit computer there. So you go down to 16 features.
Good. Any other question?
Maybe one like I didn't really understand. I thought the goal of the paper was to generate peptides that will bind to that will bind to their trash so they can like improve ecologies and stuff. But they don't talk about generating peptides. They just fit on data. So how will
I
you
think the binding affinity score is to the plastic. Isn't it? I guess so.
it's plastic.
So how they generate new peptides then? Like do they just give a random peptide sequence?
No, it's done by autoencoder. So it's done by the classical computer that I don't explain.
Okay.
So in the latent space, it's a kind of distribution. So we sample from it, and then we can then convert it to the peptide using autoencoder.
we have decoder.
Okay.
Yeah. So in that way, and we can know the design of peptide. So it's like some fake data generation.
Okay. Okay.
Any other question? Oh, and Ooh, it was challenging, but at least we learned something, right? So let's thank the Dr. Huang.